Hi, let's start the presentation for basic concept and series of filters. I will proceed with the presentation edition TOC. This chapter 3 describes basic concepts and theories that form the foundation for design of general RF and microwave filters, including microstrip filters. We start with defining some parameters before the start. The transfer function of a two-port filter network is mathematical description of network response characteristics. On many occasions, an amplitude-scale transfer function for a lossless filter network is defined as equation 3.1. In here, omega equal Ripple constant, Fn equal filtering or characteristics function. For linear time invariant networks, the transfer function may be defined as a relational function, that is equation 3.2, where MP and dp are polymer in a complex frequency. Variable p equals sigma plus j. For a lossless specimen network, the neighbor frequency sigma equals 0 and p equals j. The sigma plane, where a relational transfer function is defined, is called the complex plane or p-plane. The horizontal axis of this plane is called the real or sigma axis, and the vertical axis is called the imaginary or j-ohm axis. This slide about Butterworth response. The amplitude scale transfer function for Butterworth filter, which have an insertion loss equal 3 dB at the cutoff frequency ohm C equal 1 is given by equation 3.7. Our relational transfer function constructs from equation 3.7 is equation 3.8. The shape response that exhibit the equal ripple passband and maximally flat stopband is depicted in figure 3.3. The amplitude scale transfer function that describes this type of response is equation 3.9, where the ripple constant sigma is related to a given passband ripple loss insertion loss in dB by equals 310. Tn is Chebyshev function of the first kind of order n, which is defined as equation 3.11. Hence, the filters realized from equation 3.9 are commonly known as Chebyshev filters. The response, which is equal ripple in both the passband and stopband, is the elliptic function response as illustrated in figure 3.5. The transfer function for this type of response is equation 3.13a. Where ohm more than 0, smaller than 1, and ohm more than 1 represents some critical frequency m and n are constants to be defined by 3.13b. The Gaussian response is approximated by a relational transfer function as equation 3.14, where p equals sigma plus j ohm is the normalized complex frequency variable, and the coefficient as equation 3.15. Figure 3.7 shows two typical Gaussian response for n equals 3 and n equals 5, which are obtained from equation 3.14. In general, The Gaussian filters have a poor selectivity, as can be seen from the amplitude response in figure 37a. With, with increasing filter order n, the selectivity improves little and the insertion loss is decibel. Approach the Gaussian form as equation 3.16. Use of this equation gives the 3D bandwidth as equation 3.17, which approximation is good for n more than 3. Hence, unlike the Butterworth response, the 3D bandwidth of a Gaussian filter is function of the filter order. External group delay equalizers, which are realized using all-pass networks, are widely used in communication systems. The transfer function of an all-pass network is defined by equation 318, where P equal omega plus j ohm is the complex frequency variable and Dp is a strict Hertz polynomial. Filter synthesized for realizing the transfer function, such as those discussed in the previous section, usually result in the so-called low-pass prototype filters. For example, figure 310 demonstrates two possible forms of an n-pole low-pass prototype for realizing an all-pole filter response, including Butterworth-Chebyshev and Gaussian responses. For Butterworth or maximally flat low-pass prototype filters having a transfer function given in equation 37, with an insertion loss equal 3 dB at the cutoff ohm C equal 1, the element values as referred to in figure 310 may be computed by equation 324. For convenience, table 3.1 gives element values for such a filter having n equal 1 to 9. As can be seen, the two-port Butterworth filters considering here are always symmetrical in network structure, namely G0 equal Gn plus 1, G1 equal Gn, and so on. To determine the degree of a Butterworth low-pass prototype, a specification that is usually the minimum stop band attenuation. For Chebyshev low-pass prototype filters, having a transfer function given in equation 39 with a passband ripple insertion loss and the cutoff frequency equal 1. The element values for the two-port networks shown in figure 310 may be computed using the following formulas as equation 326. Figure 311 illustrates two commonly used network structure for elliptic function low-pass prototype filters. In figure 311a, the series branches of parallel resonant circuit are introduced for realizing the finite frequency transmission zeros, since they block transmission by having infinite series impedance at resonance. The basic network unit for realizing all-pass, low-pass prototype filters is a lattice structure, as shown in figure 31112a, where there is a conventional abbreviated representation on the right. This lattice is not only symmetrical with respect to the two ports, but also balanced with respect to ground. By inspection, the normalized two-port Z parameters of the network are equation 331. The network elements for a single section D-type low pass prototype, as shown in Figure 312C, are given by equation 330. Higher order all-pass prototype filters can be constructed by a chain connection of several C and T-type sections. This chapter is about low-pass transformation. The frequency transformation from a low-pass prototype to a practical low-pass filter having a cutoff frequency in the angular frequency axis omega is simply given by equation 337. Applying equation 337 together with the impedance scaling described above yield the element transformation as equation 338, which is shown in figure 13a. For high-pass filter with a cutoff frequency is omega c in the omega axis, the frequency transformation as equation 339. It is then obvious that an inductive or capacitive element G in the low-pass prototype will be inversely transformed to a capacitive or inductive elements in the high-pass filter. With impedance scaling, the element transformation is given by equation 34T. This type of element transformation is shown in figure 314a. Assume that a low-pass prototype response is to be transformed to a bandpass response having a passband omega 2 minus omega 1, where omega 1 and omega 2 indicate the passband edge angular frequency. The required frequency transformation is with equation 341b. The elements for the series LC resonate in the bandpass filter are equation 342a, where the impedance scaling has been taken into account as well. Similarly, the elements for the parallel LC resonator in the bandpass filter are 342b. The bandpass element transformation in this case is shown in figure 15a. The frequency transformation from low-pass prototype to bandpass is achieved by the frequency mapping as equation 343, where omega 2 minus omega 1 is the bandwidth. The bandpass element transformation of this type is shown in figure 316a. Okay, that's it. Thank you for listening.